So today we shall look at some ways of characterizing the data without using all of the entries. So as an example, here in columns A and B, I have some statistics for coronavirus cases in Uzbekistan for last 10 days. So you can see here we have a date and the new cases for that date. Like on 1st June, there were 79 new cases registered and so on. And you can also see that each day we have different numbers. Yeah, one day there are more new cases, the other day there are less, and so on. But there is a way of describing the overall average trend. So like we can just average over all of these numbers, and for that we will just add them up. We will find their sum. So let me do it here. So we should add up all of the above numbers, and we have 10 of such numbers. So we just take the sum that we just calculated and divide it by 10. And what we get is the, well, in everyday life, we will say average number of new cases for last 10 days. But as you will see, there are different types of averages, different kinds of averages. And this one is called the mean number. So that's the mean number, excuse me, the mean number of new coronavirus cases in our country for last 10 days. We can say and be more or less correct at that each day we have 92 new cases. In fact, that's not true. You can see that there are days where we have much less than 92, and there are days we have much more than 92. But on average, we have 92 new cases each day. And that kind of average, the arithmetic average, is called a mean number. So the mean value is just the, well, I refrain from using the word total.
Teacher?
Sum of all the entries divided by the number of entries. Yeah, just a moment. So you have a question?
Yes, for interruption. One student said that there is no electricity, so he's unable to join.
Can you please repeat more low to yes?
There is one student who said that there is no electricity, so he can't join to the Zoom session. Can you take that into account?
I see. Well, sure. Anyway, the attendance is checked not by your participation in Zoom conferences. University uses your participation in Canvas discussions to judge your attendance. So even if you were not online for the lesson itself, you will be counted as, so your attendance will be, well, how do you call it?
Yeah, sure, I got this.
Yeah, so if you are there in
Thank you.
session, then it's okay.
Okay.
Okay, dear teacher, good afternoon. Can you record the lessons, please?
Oh, I am recording.
Yeah. Okay.
And by the way,
then,
so
in this case, can you share by?
Yes, sorry.
How can you share with us through Canvas or Telegram or something?
So if you go to the Canvas announcements tab, there is a link to YouTube channel. All of the recordings are there. There is a separate playlist called Summer Statistics, and all of the recordings will be there. So the last one is not online yet, the Monday one. There were some problems converting it to, but now it's solved, and today I will upload it. And I guess this recording will also be uploaded today.
Okay, thank you, teacher.
Anytime, you're welcome. Okay, so to find the average, to find the mean value, we just add up all the numbers and then divide by the number of all the entries. So the formula looks like this, and this strange letter, which is in fact the Greek letter sigma, stands for the sum. So you imagine you have several entries in your data set, and let's denote them by x. So you add them all up, and then you divide the result by the total number of entries, which is 10 in our case. And what we get is called the mean value. So it's usually denoted as over bar. So if, for example, if your quantity itself, if you choose to mark it as A, then your average will be A bar. That's just a notation. So you add them all up and you divide it by the total number.
Teacher.
Yep.
I'm sorry, can you please repeat the explanation of this formula?
Okay, so this symbol here, I guess we can do it in a slightly different way. So just a moment again. I should have pre-connected, but whatever. So let me check if it's working. Oh, it does not seem to be working. Oh, okay, here it is. So this one stands for the sum. Oh, the technical problems. Yeah, so this guy here just means that you should add all the entries up. It's the sum. And yeah, there is a slight displacement, but I guess you understand where it's pointing. So X is just our numbers.
Isn't this like finding the average number?
Yeah, we want to find an average number, and this formula is just a shorthand for finding an average number. That's your entries. It's not going to synchronize properly, but okay. So that's your entries. So in our case, these are the numbers of new cases, and N is the total number of entries. Yeah, for some reason, it's being shifted after I enter it, but okay, whatever. And this thing here, the X bar, is just our average or our mean. So we use the term mean value in statistics. So you just add all the numbers up and then you divide by the total number. And that's all, in fact. Okay, let's move on.
Thank you. I
Let's
saw
go
there
back
is
to our...
mean, I mean minimum value.
Oh, no, mean as an M-E-A-N.
Yes.
Yeah, here it
Thank you.
is. Mean. Okay, so here we know each number and we can just calculate the mean. What if we don't have exact numbers? So here, it's also the data for coronavirus cases in Uzbekistan. However, that's not the data for 10 days or 5 days or 6 days, that the whole data starting on 15th of March. And instead of giving you long list, so here is the full list if somebody is interested. As you can see that it's there are entries for each date and so on. But there are way too much numbers. There are 87 of them. And instead of listing each one, I made a frequency distribution here. So we have, well, just as an example, we have only two numbers which are between 120 and 160. And we can check that if you want. So we have, okay, let me find those entries. Yeah, we have 133 here and 137 here. And we have only one number which is between 200 and 240. And it's right here on 7th of June and so on. So we have this table. We don't know each number. So we have seen that these two numbers, which are between 120 and 160, are 133 and 137. But we know that because we have the full data here. And if we didn't have the full data, we wouldn't know which exact numbers are here. But we still can calculate the mean. And let me show you how exactly do we do it. So first I will find the midpoints of each interval. So here it's 20, right in between 0 and 40. Here it's 60, 100, 140, 180, and 220. Oh, and you know what? I better insert a new column here and put them, yeah, wrong place. So let's put them here. Okay, so I don't know exactly what two numbers are between 120 and 160. But I can, with some level of credence, I can assume that both of those numbers are close to 140. So I will just say, okay, I don't know which numbers are there, but I'm just going to pretend that both of those numbers are 140. So we have two 140s. We have one 180. We have one 220 and so on. We have 37 entries of 20. That's not totally correct, right? If we check the true data, we can see, for example, that this one, which is between 200 and 240, is not 220. It's 237. But nevertheless, I can use these, what do we call it, approximations, and calculate an approximate mean value. So how will I do it? I will multiply each midpoint by the frequency. So 20 times 37, 60 times 37, 100 times 11, and so on. So it's column M times column N. So I will multiply all of them, and then I will find their sum. So sum of all the products, and I will find the sum of all the frequencies. And I will divide this by this. Sorry. So let me do it. We divide on 8 by N8. So 53.2. That should be kind of close to a true mean value. And in fact, so, okay, it's not showing on the screen, but yeah, let me just switch. Is it here? Almost. Yeah, it's here. So all the data is here. I just sorted it. We have 89 numbers. It's the same data. And let me calculate the true average value, the true mean. And you will see that it's indeed kind of close to what we get there. So it's 51.6. It's 51.6, and here, oh, yeah, I chose the wrong one, sorry. Just a moment. It's here. So we got 53.2 from this approximation, and the true one is 51.6. I'll write it down here. So they are close to each other. However, here, instead of working with 89 different numbers, we only used 6 of them. So our job was made kind of more easy by using this frequency distribution. And we still get the result, which is good enough. Like there is only 2% difference between these two, or maybe 4%. It doesn't matter. They are close. They are very close. And when you have large data sets, and in real life use of statistics, you will have data sets of 1,000 entries, or of tens of thousands of entries, or maybe even millions if you are working with big data. And you don't want to sit there trying to add up million different numbers and so on. And in such cases, you just use your frequency distribution to find this approximate value of mean. And this kind of average is called weighted mean. Okay, I suppose I should merge these two cells. So this one is a weighted mean. So again, I'll put some substitute for a formula here. So sum of the midpoints multiplied by frequencies divided by sum of the frequencies. And that will give you your weighted mean. I think we need to make 1 or 2 more examples with that. But in the meantime, let me prepare the proper formula for weighted mean. So
Teacher, can you clarify what does weighted mean? Little bit, like.
the word itself, or what?
Yes, the meaning of the word, like why do we
Oh,
need this weighted mean?
yeah, I see. So Oh, something, for some reason my formula here is not working. I'm not sure why, but okay, so it's okay. So you see, when we are calculating just the mean, the first one, we just added up all the numbers. Like, let me go back to our window. Yeah, it's here. So we just added up the numbers themselves when we
Yes.
were calculated the mean value. And here for weighted mean, I take each number and I multiply it first by the frequency and then add up. So instead of taking just the numbers themselves, I use additional information, and I don't know the reason for this, but there is a well, what do we call it? Mathematical tradition of calling this kind of multipliers the weights. So frequencies in this case are playing the role of weights, and that's why we call the mean, this kind of mean, the weighted mean. Well, we can imagine it like that, you know. So let's say you are going to find the mean value, mean number of, oh, I don't know, maybe potatoes. So you have several boxes of potatoes, and first box contains 20 potatoes, the second one contains 60 potatoes, and so on. And if you just want to find the average number of potatoes in the box, you just add them up and divide by the number of boxes, and that will be just your simple mean.
Yes.
But if you want to find the average weight of potatoes in each box, you should multiply by how many kilograms are there or how many grams are there in each potato. So you should multiply by the weight, and you will get the formula that looks like this. And so in proper mathematical notation, the formula looks like this. So F here stands for frequencies, and X is your entries. So we multiply each entry by its frequency, we take their sum, we divide by the sum of the frequencies, and what we get is the weighted mean. So I guess I'll take a couple more examples just to be more, well, what do we call it? Confident in usage of weighted mean. So let's just generate some random numbers. I'll ask Excel to create some random numbers between maybe 2 and 10. And let there be, I don't know, maybe 10 of such numbers. Now, you know, I'll create a list of 100 numbers, and then we will use a part of it. So here we have some random numbers, and as this is discrete numbers, we can use frequency table instead of frequency distribution. And I know that there are numbers between 2 and 10. So 2, 3, 4, 5, 6, 7, 8, 9, and 10. And I'll try to find how many of each number are there. So
Teacher, we have not the Excel screen.
Yes.
oh, yeah, sorry. I forgot to switch back.
Yeah, could you explain it again, please?
Explain what?
What did you do here
What
on
you
Excel?
talking?
Okay, in a moment. Give me a moment. So I'll hard code the formula and then go back to showing what was did there. It's this one. Okay. So I just made the Excel create some random numbers between 2 and 10. There's nothing special in 2 and 10. That's just first two numbers that came to my mind. So, and I asked Excel to create 100 of such random numbers. So you can see here, it's just generating a random number in each cell, 6, 4, 3, 6, 9, and so on. And now I'm going to find how many of each number are there. I know that there are numbers between 2 and 10, so I made a neat list here of those numbers. And now I'll just ask Excel to count the numbers. So now it tells us that we have 11 pieces of 2 here. So here is the first one and 2 more. We already got 3, 4, 5, 6, 7, 8, 9, 10, 11, and that's all. Yeah, so we have 11 entries of 2, we have 9 entries of 3, 13 entries of 4, and so on. So in fact, this thing we have here is just a frequency table. So this is our X and this is our F. And what I do when I calculate the average, I add up all of these numbers, right? And I can just go like, so let me just write it here to illustrate. So I can go like 9 plus 4 plus 2 plus 7 plus 7 again plus 10 and so on, right? But instead of that, I can do this. So I know that there are 15 entries of 9 in this list. Oh, by the way, let's just fix that so it won't change each time, because otherwise it will change each time we enter something. Okay, so I know that there are 15 entries of 9. So if I go on like this, adding all the numbers, I will repeat 9 15 times. So is it not better to just go like this? So I know that there are 15 entries of 9. So I just take 9 and multiply by 15. I know that there are 15 entries of 2. Oh, okay. So this one changed. Yeah, I don't want to mislead you. So just let's redo it from the start. So here we have 2, and then 2 again, and then 2, and then 5, 7, 2, 9, 7, and so on. Yeah, and let's start with 2. So I see that I'm adding up all the numbers. I have 1, 2, 2, 3, 4 2s, and then 5, 6, and so on. And in fact, we know that there are 15 entries of 2 in that list, in that data set. So instead of just telling, okay, add up the 2 15 times, I will multiply 2 by 15. And then I have 3 10 times. So first one is here, and another 3 here, another one here, and so on. Also 10 times. So when I add up all the numbers, I add 3 10 times. So I can just multiply 3 by 10 and add it. And then I have 4, also 10 times. I have 5, 11 times, and so on. So I just take each number, I multiply by the frequency, and I add them up. So I will ask Excel to do that multiplication for me. So I multiply column C by column D. So 2 times 15 is 30. 3 times 10 is also 30, 4 times 10 is 40, and so on. I will add all of those numbers up. So all of these numbers. And I have 584. Instead, I could have added these numbers themselves, by themselves, without multiplying to anything. So let us do it too, just so that you can see that the result is the same. So if I add up all those 100 numbers, I get 554. And I get the same thing here. When instead of manually adding each number, I first grouped them up. I took all the numbers 2 first, and then I took all the numbers 3, and so on. So we have the same result here and here. Okay, now I will add up all of the frequencies. And we should get 100, I guess. Yeah, because there are 100 numbers. And if I divide this by this, so 584 by 100, I get 5.84. Now, let's just ask Excel to calculate the average using the numbers themselves instead of a frequency table. So we get the same average. So in this case, where we have discrete numbers and where we use frequency table instead of frequency distribution, weighted mean is just the same as mean. So here we have mean, and here we have weighted mean.
Yeah.
And they are same, as we can see. However, we calculated them using different approaches. We calculated the same thing, but we used different approach. So, okay, I'll create a new sheet here and just show you the gist of the method. So here, all of those numbers are mixed randomly. And when we calculate the mean, we just add this plus this plus this and so on. And when we calculate weighted mean, we do something like, no, I don't need custom sort. Okay, we do something like this. So I sorted all the numbers and I will divide it by, I will group them up just for the sake of illustration again. So the same numbers as before, I just sorted them and now I'm grouping them up. All of the similar entries. Okay, so here they are. So to find average, to find the mean, we just add all those numbers up, and then we divide it by their total number, which is 100 in this case. Or we can first add up all of the 2's, and I see that there are 15 of those. So I will have 2 times 15, and I have 10 3's, so I'll have 3 times 10, and 4 times 10, and 5 times 11, and so on. So 6 times 14, 7 times 10, 8 times 5, because we have 5 8s here, 9 times 15, and 10 times 10. So in fact, I'm still adding up all of those numbers. I'm just grouping them first. And when you are calculating the weighted mean, you are essentially doing this. Instead of adding them all one by one, you just gathered all of the 2s, all of the 3s, all of the 4s, and then added them up. And we see that our results are the same in both cases. There is no difference. So you might ask, if there is no difference, then why do that? Why do we even need it? And we need it for cases like this. So here we don't have much repetitions. All of the numbers are different, right? And instead of sitting there adding up hundreds and hundreds of different numbers, we can just take that frequency table, frequency distribution, and use the weighted mean. However, when you use weighted mean here, you get the exact same result because the numbers are exactly the same. Here you will have a difference because we are not taking the exact numbers. So here you can see that we have 37 numbers between 0 and 40. And if you want, you can go here and check what those numbers are, and you will see that they are different. So we have 1, we have 7, we have 3, we have 5, we have 10. So 37 different numbers. And when we are using this to calculate weighted mean, we are telling, okay, I don't care that those numbers are different. I will just assume that all of those numbers, yeah, there are 37 numbers, all of them are just 20, which is the middle, the center of our interval. And then you have 37 different numbers between 40 and 80. So there might be something like 52, 73, and so on. And you are telling, I don't care, all of them are just 60 for me. All of the different 11 numbers between 80 and 120 are just 100 for my case. So you are substituting the real numbers, which are there, with some approximation to make calculations easier for yourself. So you are getting the different number when you are calculating weighted mean, but the difference is small. The true mean is 51, almost 52, and weighted mean is 53, and they are very close to each other. So even though you are making a small a mistake, that mistake is very small. It's almost negligible. I don't care if there is a difference of 2 when the mean itself is 53. So that's okay for me. I saved a lot of time when instead of adding 89 different numbers, I just used this neat table with 6 rows. So even though I lost a little bit of precision here, I have saved up a bunch of time, a bunch of energy. So that's a kind of a trade-off. Okay, we are losing something here, but we are getting something in terms of calculation time. And here, that trade-off might seem unimportant, let's say. After all, adding up 89 numbers, maybe it will take an hour of our time, maybe a half an hour. So it's not a very large amount of time. But again, in real life, you will deal with lists of thousands or hundreds or tens of thousands of entries. And there, the time you win will be much more than here. And the difference will be much smaller. So when your data sets are very, very large, the difference between true mean and weighted mean is much, much smaller. So we can check it here if you want. So only 10 entries. And I don't want to create the frequency distribution manually. I'll just ask Excel to create a histogram for me, and I will use that histogram. So we have, yeah, so our first interval is between 27 and 117. And ours, yeah, let me write it like this. The next one is 117 and up to 207. And the last one is 207 up to 297. Frequencies are 9 for the first interval, 0 for the second, and 1 for the last. So that's the frequency distribution for this list, for these 10 numbers. And if I calculate the weighted mean using these, let me move frequencies here. So these are frequencies. I'll find the midpoints. So, okay, 27 plus 117 over 2 will give us the center. It's 72. And the next one will be 162. And the next one, 252. And now I will do the same what I did earlier. I will multiply midpoints by frequencies. Okay, I'll find the sum. And the sum of the frequencies is just 10. So I multiply this by 10. Okay, it will be just 90. So weighted mean is 90. And the true mean is 92.4. So you see, even though our data set is small, weighted mean is still close to true mean. So in cases where calculating the true mean will take too much time, where calculations might be tedious and boring and long and time consuming, you can just calculate weighted mean. And you can be sure that you are close to true mean. So here our data set is 10 numbers and still the numbers are close. Here we have 89 numbers and again they are close. And when you have something like 1,000 numbers, your difference will be, well, I'll just make up some numbers. Let's say you have a true mean of 15.73 and maybe you will have a weighted mean which is 7299, for example. So they will be very close to each other. But weighted mean will save you some time or lots of time. It will save you some energy and so on. I guess now we will make a break for maybe 5 minutes and then we'll come back and we will look at 2 other measures of locations. They will be easier than mean. So bear with me. Be right back. See you in 5 minutes at 1.10. Oh, what was that? Yeah, nothing. Well, so we can somehow characterize our data using mean, as we have seen, right? So for example, here, our mean is 92, about 92, and most of the numbers are more or less close to 92. However, you can see that there are two of them that are way too far. 27 for 10th of June and 237 for 7th of June. One is almost 3 times smaller. Another one is about 2 times larger. So the mean value does not always represent the entries in a very correct and meaningful way. And also, there are times where mean value is just misleading. So let me give you an example. I guess sometimes all of you either watch or read or listen to news on TV, on radio, or in some kind of online newspapers, and sometimes we get kind of ridiculous news, something like maybe the average salary in our country is, I don't know, $1,000, 1,000 US dollars. And you hear that, and then you are puzzled. Hey, most of my acquaintances, my friends, my relatives, and so on, have an income of somewhere between maybe $200 and $500. How can the average be 1,000? Well, and there's the case. So I'll take some toy model. Yeah, let's look at these 7 numbers. Let's pretend that these are salaries of different people. Yeah, so we have a bunch of people who make about 100 US dollars a month. So maybe waiters in some kind of cafes, couriers, and so on. So some underpaid jobs. And the salaries are quite small. And then we have something like a CEO of a large organization who makes 5,000 a month. And if I calculate the average here, if I find the mean, our mean is almost 800. And that's misleading. It does not represent our data very well. So there's absolutely nobody here who makes $800 a month. There's nobody who makes even close to that number. So most of our guys have much less, and there is one who is making much more. And if only I had to remove this one, if I used only the first 6, then my average will be much more reasonable. So let's do that too. Okay, so now it's 98, and if we ignore this one, 98 is very good approximation to all of these numbers. So one large number is just ruining our statistics, so to speak. It's shifting our average and making it way too high. So that's the downside to using a mean value. Mean value is very susceptible to extreme numbers, to extreme values. So if you have one or two entries which are way too high or way too low, then your mean value will go high or go low. It will go crazy. And sometimes that can be counterproductive. So it's still a mean value. It's mathematically correct, but it's not representing our data in a good and meaningful way. So sometimes using mean value, we make false conclusions, just like in the case of salaries. So when you hear statistics on mean salary in the country, you might be misled to believe that people live way better than in reality. Or it might be the other way around. You might have you might have an extreme values which are too small, so your average shifts down, and you will be led to believe that people live way worse than in reality. So that's not the case for our country, but still. So we need some way of going around that. We need to work it out. And for such cases, we have another measure of location. So here is our mean value. And now what I will do, I'll take these numbers, I will sort them. Yeah, so now they are neat and sorted. And I'll just find which number is in the middle. So there are 7 of them. So this one will be the midpoint. Not the midpoint, yeah, but it's standing in the middle. So we have exactly 3 before and 3 after. And this number is also a measure of location, and it's called a median number. It's called a median number. By the way, let's use the inbuilt Excel instruction for that. Okay, so median is 100. Mean is almost 800. So in this case, median is much more representative of the true data. And also, what happens if I change this 5,000 by, for example, I don't know, what if I make it 200s? So you can see that mean went down, but the median didn't change. So that's the, well, what do we call it? That's where the median comes up. So mean is susceptible to extreme values. Median is not.
Could you explain one more time what is median?
Sorry?
Could you explain one more time what is median? I didn't understand. How did you get 100?
Oh, well, I did it right now, but okay, let's just repeat that. So when you calculate the mean, you use all of the numbers, you add them up, you divide by their total number and so on. When you want to find the median, you just put your numbers in order. Yeah, so I sorted them here. And then I just take whatever is in the middle. So for example, if we had only 3 numbers, maybe 1, 5, and 100, then our median will be 5 because it's in the middle. So whatever is in the middle is your median. That's
what about
neat.
4 numbers?
Yeah, that's the next thing we should look into. So what if we have 4 numbers or 6 numbers or 100 numbers? So let's make an example. I don't know, I'll just put some some numbers out of thin air, maybe 40, okay, 50, 52, and 100. So there's no number in the middle. Or in other words, there are two numbers in the middle. I just take the average of those two. So 50 plus 52. Okay, I forgot the parenthesis. Divided by 2. And that will be our median. So 51 in this case. Let's check that. Let's ask Excel to find the median. Yeah. So if you have a number, one number in the middle, then it's the median. If you have two numbers in the middle, their average is the median. However, you must sort the numbers first. So if I go with unsorted numbers, I'll get wrong values for median. Let me go back here. Let me take these numbers. I'll copy them. And use them as an example. So we have 10 numbers here. We don't have one number in the middle. There are two of them. So we should take the average of these two numbers. 68 plus 87 divided by 2. So 77.5, but it's not a median. If I calculate the median, it's 81.5. And the reason we get a wrong result is because we did not sort the numbers. So I need to sort them first. They should be in order, either ascending or descending, it doesn't matter. So let's sort them ascending. So now I see that there are, so numbers in the middle are 80 and 83. So if I fix that, 80 and 83, now it's correct. So to find the median, you should sort all your numbers and then you take what is in the middle. So finding the median is much easier than calculating the mean in some way. And median has its own upsides. So median is not susceptible to extreme values, for example. So when you have the median, you can be sure that most of the numbers are close to median. When you have mean, you can't be sure about that because your mean value is, I lost the word. Your mean value changes according to your extremes, like here. Where is the median and where is the mean? And also, if you know both the median and the mean, you can convey some useful information from that. So whenever your mean and median are close to each other, you can be sure that your data are more or less symmetric. So I guess I will make a picture for that. Well, I'm not sure if that will be possible now, but let's try. Let's go to the whiteboard. Yeah, here it is. So okay, it seems, yeah, I need to switch the device itself. I hate it when it happens, but just give me a moment. So I guess I can use this. I need to clear it first. Okay. Oh, why is it not possible? Huh? Yeah, nice. Nice. So here it is. Here it is. So I'll use a plot. So let's say your data is something like this. You have a bunch of numbers in the middle. You have some large numbers, some small numbers. And in this case, your median will be approximately equal to mean. So they will be close to each other. If your mean is higher than your median, it means that you have way more small numbers and several large numbers. So there are lots of numbers in here which are small, and there are one or two extreme values here. So your data is asymmetric. You have something like in our example where you have a bunch of people getting 100 and one man or one lady getting 5,000. Well, and if your median is more than your mean, or if your mean is less than your median, then you have it the other way around. It means that you have a bunch of large numbers and one or two extremely small numbers. So a relation between the median and the mean shows you if your distribution is, what do you call it, symmetric or not, if it's skewed or not. There is a word for that. We say that the data distribution is skewed to the right or skewed to the left. And you can see it on your plots too. So right here, the histogram shows us that distribution for these numbers is skewed. We have a large number of small entries, yeah, between 27 and 117. And we have very few large entries, only one in fact, 237. Or if you do the same for example, for these numbers, so let me insert the histogram. Okay, I see that it's more or less the same everywhere. However, still there are a little bit more small numbers than large numbers. So if I find the median, it should be a bit less than the mean, but they have to be close. So we know our mean already, it's 5.84. And now I will find the median too. And it's 6. Oh, it's a bit more. Oh, well, that's strange. That's strange, but okay. Oh yeah, we can see it here too. 6 is right in the middle, on the boundary between the two. Well, but still that's strange. So we have 35 plus 25, 60 numbers which are less than 6, and we have 25 and 15, only 40 numbers which are more than 6. Okay, maybe we have just a number of sixes. So let me sort the data and check it. So numbers 50 and 51 should be, yeah, the median should be 4. For some reason, it's calculating the median incorrectly. So we start with A17 and we go, no, sorry, I'm mistaken, 67 and 68. Yeah, it's 6. It's 6, it's all right. Okay, so that's a strange quirk, but it happens sometimes. But anyway, you can see that the difference between the median and mean is not so much here. And that's because we don't have the strong asymmetry. We have almost the same everywhere. While here, there is a clear skewness, and if I find the median for this data set, oh, we already did that, didn't we? Yeah, it's 81.5, and it's much less than 92.4. The difference is large. So I'll add the median in here. 81.5. Yep, good. Okay. Okay, so that's the median. So if I want to take into account all of the numbers, I better use mean value. But if I know that there are extreme values which can break my statistics, which make my distribution skewed, like here, I better use the median because the median will be more representative. And the best way is using both. When you have both, so both the mean and median, you have a good representation of your data, and you also can judge about its shape, whether it's symmetric or not, are there extreme values or not, and so on. So here I see that the difference is large, and I can be sure that there are extreme values. And I even know that they are extremely large values because the median, the mean is much more than median. When there are no extreme values, mean and median become more close to each other. Okay, and then we have another measure of location, which is called mode. Now the mode, well, we better use the example, I guess. Hey, what are these numbers? Okay. Yeah, it's all right. So I'll use this data for mode. So I see that I have 15 entries of 2 and 15 entries of 9 here. And all the others are less. So there are 14 sixes and 11 fives and so on. So for this data, I have 2 modes. One of them is 2 and the other one is 9. So whichever number you encounter more is the mode. So for example, if we have something like maybe 1, 2, 3, 2, 5, 2, and 10. Yep, so if this is our data, then our mode is 2, because I have 3 entries of 2, and all the others are less. Only 1, 3, only 1, 5, only 1, 10, and 3 2s. If I have something like, maybe like this, I have 2 modes now. So one mode is 2 and another mode is 1, because both 1 and 2 are encountered 3 times, and all the others, which is just 10 in this case, are less. And if I have something like this, where I have 3 ones and 3 twos and 3 tens, so the frequencies are the same for all of them, then I have no mode here. So I'll be forced to remove this. There isn't a mode when.
So this is kind of the frequency.
Yep. So the mode is whichever entry has the largest frequency. And if all the entries have the same frequencies, then you don't have a mode. Frequency is just how many of them are here. So I have 1, I have 2, I have 10. And if I count, I have 3 entries of 1. So the frequency for 1 is 3. And frequency for 2 is also 3. And frequency for 10 is also 3. So when they are all the same, you have no modes. When you have a leader, so I'll remove this 2, and then frequency for 10 is just 1. Now we have 2 modes, 1 and 2. If I remove one of these ones, like that, for example, so now frequency for 1 is just 2. Now we have only one mode, and it's 2. So you find the frequencies and the entries which have the maximum frequencies are your modes. So I'm sure you are familiar with the Russian word moda, which means fashion. It also means mode. And fashion and mode have deep connections, in fact. So what is fashion? Fashion is what most of the people choose to wear, so to speak. So if you find the frequencies for different kinds of clothing, then the fashion is whatever has the largest frequency. So fashion is the mode of clothing. And I guess that's the reason why in Russian you use the same word for mode and for fashion. Okay, so we have 3 measures of location. One of them is mean, and the mean value is something that's calculated using all of the entries. So change any one of them and you will change your mean. Then we have the median, which is not dependent on the entries themselves, only on their positions. So if you change your outlying numbers, the smallest ones or the largest ones, your median will not change. If you change something in between, then your median might change or it might not. But the thing is that it's not dependent on those border values, the smallest and largest ones. And then we have the mode, which is just whatever you have more here. Mode can also change when you change some of the numbers, like here. So if I change this 2 to 3, then all of a sudden I have 2 modes instead of 1 mode, 1 and 2. If I bring that 2 back, I have only 1 mode and it's 2, and so on. So that's the 3 measures of location. And speaking of median, we have to look at one more thing. So let me take this again as an example. So I already know that my median is 81.5 because it's right between 80 and 83. And I can now divide my data. I will use colors for that. So all of the green ones are less than median. And all of the pink ones are more than a median. So now I can just treat this half as the separate data set and find its median. So median for this green half is 68, right? And the median for the pink half is 96. And those have their own names. So median of the first half is called first quartile. So you have first quartile, or simply Q1. And then you have third quartile, Q2, Q3, sorry. And your median, so the second name for your median is second quartile, Q2. So you see, the median divides your data into two pieces, and quartiles divide your data into four pieces. So I'll make it, again, I'll use colors. I'll save the same colors, so green for this one. However, I'll make gradations of brightness. So brighter green, darker green, and so on. And the same here. Okay. Okay, here we go. So median divided our data into two, so the green part and pink part, and quartiles divide our data into four. So this two is one part, this two is another part, the next part, and the fourth one. So there is a use for quartiles. So let me do one more thing. So if I go here and look here, I should have, yeah, here it is. So this thing is called a box plot. It's called a box plot, and I guess making it larger will be beneficial for us now. So for now, I want pay attention to this dot over here, and I will focus on this part. So you can see the line in the middle here. We can't know its exact value looking at the picture, but I know that it's 81.5. It corresponds to 81.5. This line is your median. Then you have your box here. So boundaries of the box are your quartiles. This is 96, so your third quartile, and this one is, it should be 68, which is your first quartile. This here, the end of the whisker is your minimum, which is 27. And this end of the whisker looks odd, but again, I know that it's 109. And this dot over here is your 237. So why is it separated? I guess it will be a bit more clear using this. Yeah, let me bring back my 5000. So looking at this, you just intuitively know that this number is different, right? It's breaking your data. So these ones are all close to each other and neat and so on, and this one is way too different. and you just see it. However, sometimes it's harder for us to perceive which number is breaking the rules, so to speak. So here, 237 is such number. It does not comply to a trend given by these numbers. It's just like that 5,000 guy there, 237. And our box plot shows that thing to us. But how does it know that this is different, 2 and 37? So there is a thing. So there is a thing called IQR, interquartile range. I'll write down the interquartile range, and it's just quartile 3 minus quartile 1. We can calculate that for our data. So it will be 96 minus 68 in our case. However, I better use links instead of the numbers themselves. So this minus this. So it's 28 in this case. Now, if you take the median and add 1.5 IQR, and subtract 1.5 IQR, you get the boundaries. So let us do that. We take a median minus 1.5 times IQR, and here we take a median plus 1.5 times IQR. Okay, so what do those numbers tell us? Oh, that's strange, by the way. Am I mistaken? Should it be 2.5? Let me check. Give me a moment, please. So maybe that's 2.5. I have to check. But it was 1.5. Okay, anyway, I better check that because I don't want to mislead you guys. Okay. It has to be somewhere here. No, it's not here. Okay. It's here. Quartiles. We don't need percentiles now. Yeah. Yeah, it's 1.5. Okay. Okay, so I did not make a mistake. So what do those two boundaries tell us? Whatever is less than 39.5 or more than 123.5 are outliers. They are breaking the data, right? So 237 is more than 123.5, and that's why it's noted as this, as separate dot, instead of sitting on this whisker. However, 27 is the same. It should also be marked as an outlier. For some reason, Excel did not mark it, but it should have. And we can check that if you want. So if I change 237 into 120, for example, then my box plot here changes, and you see there is no dot. Now the whisker is ending at our 120. if I make it 125, that's enough to make it more than this boundary. Yeah, but Excel is not doing that. Maybe Excel is using slightly different formula. I'm not sure. Let's try with 2 IQ error. The standard in statistics is 1.5 IQ error, but it might be that the Excel's realization of box plot is different. So maybe it should be 2 here. But whenever you do it on, for example, maybe on exams or something like that, you use 1.5 IQ error, not 2. Now I'm just checking 2 to see if that's what the Excel uses. So 138 should be enough. It's not. Strange. 140? No. Yeah, there are some shady things going on with Excel, and I'm not sure what and why. But okay. Maybe that's 2.5. So 152. Okay, and what if I take 151? Now that's strange. Excel is not using 1.5, it's not using 2, it's not using 2.5. I don't know what it's using, but the rule is 1.5 of IQR. So whatever is outside those boundaries is called outliers. So 237 here is an outlier. An outlier means something that is different from most of the data. 27 is also an outlier. This one is too small and too large, and this one is too small. Clearly, 5,000 here is also an outlier. And we can even check it if you want. You can find the quartiles. It will be easy here. The quartiles are 90 and 110. You can find the interquartile range and check, and you will see that it's clearly more. So interquartile range is 110 minus 90, it's 20. 20 times 1.5 is 30. So whatever is more than 130 is an outlier, and whatever is less than 70 is also an outlier in this case. Okay, so that's the use for your medians and quartiles. And one more thing. So we have first quartile and third quartile, 68 and 96. Half of your data is always in between those two. So we have how much? 10 numbers here, and that means that there are 5 numbers between 68 and 96. In fact, if you count them, there are only 4, but that's because you should include either this one or this one. The choice is yours. So half of your data is always between quartile 1 and quartile 3. A quarter of your data is less than quartile 1, and quarter of your data is more than quartile 3. So if we look here, we have the same amount of numbers in here, in this whisker, as in this one. They are just crammed into smaller space and so on. Okay. Yeah. Hell of a lot of info for one time again. So I guess at this point we will stop. So we have our mean, we have our weighted mean and median and mode and quartiles, and that's enough for today. I highly recommend you to either read up the corresponding topics in the textbook, or maybe watch some online video lectures or something like that. Again, Han Academy will be a very good place to do that if you want, and it's free. But that's all for now. And I think we will stop there. Any questions?
No questions.
Okay.
No,
Later
it was
today, I will
understandable.
upload the Monday's recording and hopefully today's recording too. And either today or tomorrow, I will put this week's discussion. Next week, we will look at the measures of spread of dispersion. So the range, the variance, the standard deviation, and so on. Okay, thank you.
Okay.
Thank you.
Thank you. Bye-bye. Have a good day.
Thank you,
Thanks for
teacher.